and record. Okay, so we're on the third class, and today we're going to start talking about semantics and how to define the semantics of data on the web. So the lecture is on RDF schema in particular. So the last time we spoke about how, roughly speaking, we could build a semantic web based on data, logic, query, and output. So we spoke previously about RDF as a data model based on a directed labeled graph where we have triples, and each triple forms an edge in this graph. So within RDF, we have two types of terms that are of importance. So we have properties that are used as the labels of the edges to denote the type of relation between the two resources. And we have classes, which are used to conceptually group resources. For example, we have movie, actor, series, and we can associate instances with those classes. For example, to say that Sharknado is a movie, Sharknado 2 is a movie, and so forth. So today we are going to start to focus more on the logic part of the semantic web, where we'll look at a standard for defining the semantics of classes and properties. So rather than using rules like this on the semantic web, which we could do, and there are proposals for using rules, a more standard way of representing logic like this on the semantic web is to use RDF itself. So instead of using rules, what we can use is RDF, and we can use edges or relationships with special defined meaning. So we can use these edges, these relationships, to define classes or properties. So this will become clearer in a second. So if we look at a bunch of classes here and a bunch of properties here, we might ask what kinds of relationships might be useful to define between the following classes and properties. So we see, if we look at the classes, we see that some of the classes intuitively have some sort of relation between them. So for example, we see city and town, country, place, person, capital, city. So intuitively, we might imagine that there's some sorts of relations between capital, city, and city, or between city and place, or between country and place, and town and place. Full person, maybe not so much directly. We have properties: has capital, city, part of, has city, full family name, geographically part of. And we might imagine again that there are relationships between these different properties. For example, has capital city and has city, okay? Geographically part of, and so forth. Also, there might be relationships between properties and classes. For example, has capital city might have some relation to capital city, for example, or to city. So we're going to look at 4 different types of relations that we can define between classes and properties. So the first is a class hierarchy, which is relatively intuitive. We can say that a class C is a subclass of D. So then if we know that class C is a subclass of D, we know that if X is an instance of C, then we can somehow assume or entail, this will infer that X is an instance of D as well, okay? So for example, if capital city is a subclass of city, and if Dublin is a capital city, then we can define that Dublin is of type city. So if we look at this and we ask which classes would be subclasses of each other, we might guess that, for example, we already have one here, capital city is a subclass of city. So we could connect capital city to city. Oh, we started with a different one. So we could say town is a subclass of place. We could say city is a subclass of place. Country is a subclass of place. Capital city is a subclass of city. Can anyone see another subclass relation? So intuitively, if capital city is a subclass of city and city is a subclass of place, we might imagine that we can somehow, we have this implicit subclass relation to place, right? So capital city is implicitly then a subclass of place as well. Okay. So this is the subclass relation, which is between pairs of classes. Very similar concept we can apply to properties. We can define property hierarchy. So we can say a property P is a subproperty of property Q. So then we have if X, P, Y, then X, Q, Y. Okay. So for example, if has capital city is a subproperty of has city, and if Ireland has capital city Dublin, then Ireland has city Dublin. So which properties would be subproperties of each other? Well, we already have one example here, which is that has capital city is a subproperty of has city. So we can say that there's there is a subproperty relation between these two properties. Okay. Any other ones? So we could say maybe that has city is a subproperty of geographically part of. Okay. If X has city Y, then X is geographically part of Y. We might say geographically part of is a subproperty of part of. Okay. Any other ones? So like we had for subclass, we have other implicit relations here. So has capital city and has city. So if we have a subproperty B subproperty C, then we have a subproperty of C, and so forth. So we can connect has capital city, which is already implicitly connected, but we can connect it to geographically part of. So has capital city subproperty of geographically part of. Has capital city subproperty of part of. Has city subproperty of part of. Okay. So we have two more relations, and the next two relations are between properties and classes. So we say that property P has domain class C. Given that property P has domain class C, then if X, P, Y, we can imply that X is of type C. Okay. So if that property is defined for an instance, then we know that that instance is a member of the domain class. So for example, if family name has domain person, so what is FOF, by the way? FOF is a standard vocabulary that we use on the semantic web for describing people. So it's a namespace that defines some personal information about people. So if we have that family name has domain person, and if we have that Aiden family name Hogan, then we have Aiden type person. Okay. Because I have the property family name defined, we can, and because that property has domain class person, we can then infer that I'm a person. So what's important to note is that it doesn't assume that I'm defined to be a person. It doesn't check that. Rather, it will infer that I'm a person. Okay. So which properties would have which classes as domain? So we see we already have one example here, which is family name has domain person. Okay, so we can connect those two and say family name has domain person. Any other examples here? So let's say has capital city. So if a resource has the property has capital city defined, what would that make it? We could say that maybe it's a country, but also a capital city could be a state, a county, a region. Okay? So we don't want to imply that every resource that has a capital city is a country. So this is maybe an arguable definition, but probably we don't want to include it because then we can only use this property on things that are countries. Part of, there doesn't seem to be a natural one class here that would be the domain. Rather, it would be something like the union of all these classes or any possible class, which we can't define yet. If we were to connect part of to all of these classes here and say that part of has domain town, part of has domain city, part of has domain country, then every time we use part of on a resource, we would imply that that resource is a town, a city, a country, a place, a person, a capital city, which is not what we want. Okay. What about has city? Again, we might want to use that for a state, not just a country. We might imagine that this would be a country. It would be the most natural option here, but it could also be a state, a county, and so forth. Example, geographically part of. Does that have a natural domain here? Well, we could probably infer that if something is geographically part of something else, then that thing is a place. It's a location somehow. So this one seems relatively safe to define. So we can define geographically part of as domain place. So what about the range of properties? So we saw the domain. What about the objects of properties? So we can define a range such that if property P has range class C, and if X, P, Y, then Y is an instance of C. Okay. So take an example. If has city has range city, and if Ireland has city Dublin, then Dublin we can infer it to be an instance of city. So again, which properties would have classes as range? Well, we've already seen one, which is that has city has range city. So we can connect has city to city here and say that the range relation holds from this property to this class here. So what else could we look at? Let's look at has capital city here. If we look and we think, what is the range of has capital city? Can we infer a type for the objects of this property? We could imagine that the objects of this, the values of this property, let's say, are capital cities, right? So we can define the range here. Okay. What about part of? We have the same problem for part of as we have for domain. The value of part of could be a town, a country, could be maybe a person. I don't know what the subject would be in that case. Maybe a couple or something like that, or a group. But so it could be a value, could be of any of those types. But if we connect this property to all of those types, then we would infer that every value of part of is a town, a city, a country, a place, a person, and a capital city, which is not what we want. So we're going to have to return to that later. Full family name. So probably this would be a string, but we don't have that option here. The domain would be a string, or the range would be a string, sorry. Geographically part of, well, we could imagine again that the value geographically part of would probably be a place, at least. Seems relatively safe to define. So any other ranges that are possible? Well, if has capital city, if we know that the value must be a capital city, then we know that the value must be a city as well, right? So in some sense, so for example, if has city has range city, then we know that, and city is a subclass of place, then we know that the value of has city must also be a place as well. So somehow we're implicitly also defining the range to be place. In the case of has capital city, we implicitly define the range city as well, because we know if the value is a capital city, then the value must also be a city, which sort of gives us this implicit range here. Likewise, has capital city implicitly has place. So any questions or comments? Nope. Okay, so we have a trade-off when we define the semantics of terms in data between being more specific and being less reusable. So more specific allows us to derive more conclusions if we provide more specific definitions and more specific semantics. But being more specific makes the properties that we define less reusable. Okay. So we somehow want to strike a balance between these two worlds. So sometimes we might often be more specific, knowing that it will reduce the amount of reuse that we can have of the term. Other times we might want to be not be specific at all, even if it seems we could define some semantics because we want broad reuse. So for example, we already mentioned this idea that we could have defined that has capital city, has domain country, right? Which seems to be relatively intuitive. So the pro is that we would then know that anything that has a capital city is a country. So we could infer more data by this definition. But the downside of this definition is that we cannot then use this property for capitals of states and regions and so forth. So somehow, if we provide very specific definitions, that's very useful for inferring and tailing, knowing more data. But it restricts the reuse possible for that term, the scenarios in which it can be used. Okay, so as another example, we might intuitively, for example, define that a mayor is a person. So if someone is a mayor, then that someone is also a person, which seems relatively safe, right? But we might want to consider that there are many instances of animals being elected mayor. For example, Bosco the dog, who was mayor of Sunderland, California from, or lived, I'm not sure if he was mayor or lived from 81 to 94. So if we define that mayor as a subclass of person, then we wouldn't be able to say that Bosco the dog is an instance of mayor, because that would come with the implication that Bosco the dog is a person. As another example, we might define that a spouse has domain or range of person, which would limit, for example, marriages between animals, but also, for example, Rika Eiffel married the Eiffel Tower in 2007. So this is also defined, for example, in Wikidata. So if we define that the spouse has domain range for person, then either we couldn't use, essentially we can't really use that property then for this sort of relation here, because we would infer that the Eiffel Tower is a person. So when we deal with the real world, there are often or almost always exceptional cases to our definitions. So we need to somehow maybe consider this trade-off between being more specific and less reusable, particularly on the web. Also, another lesson that we've learned from the first years of the semantic web is to be aware of hidden definitions. So for example, the FOF vocabulary that I mentioned earlier, it's a very popular vocabulary. What's a vocabulary? It's a set of terms, a set of classes and properties, and maybe even instances used to describe a domain. And often the goal of a vocabulary is to get as many people to use it as possible, so that the data that use the same vocabularies become easier to integrate. So the FOF specification has this property called FOF image. And it says that the domain, having this property implies being a person. So if I have an image, then I am a person, right? And the range is that every value of this property is an image. Okay? So the range is pretty intuitive, but the domain is arguably an instance of what we would call a sort of hidden semantics, right? So in terms of the potential problems, if we were to intuitively define, for example, that a city has an image of the city at night, right? Dublin image, Dublin night, .jpg, then we would infer that Dublin is a person, right? So we should try to choose the names of properties and classes carefully. So the point here being that then we should really call this personal image or profile image maybe, or something that indicates that the domain of the property is a person. So it seems intuitive just to write a triple like this, but then this would give these unintended inferences. And this happens a lot, right? So people just take a property that seems to have the label or seems to have the name of what they're looking for, the relation they're looking for, and use that without really maybe checking the semantics. So we want to try to avoid these sorts of cases. Any questions or comments?
Sí, profesor. Entonces, ¿cuál es la respuesta correcta para darle una imagen a una ciudad, por ejemplo?
So there would be other properties. So in general, we will talk more about that in class 7 or class 8, about all the vocabularies that are available and how to find the right ones. Do I know what property to use? schema.org, vocabulary defined by Google and Microsoft and so forth, have defined these, have defined a vocabulary which has schema image. You could use that, for example. I think FOF also has a property called FOF depiction, which can be used on anything. It doesn't have a domain. So FOF image is a sub property of FOF depiction, and you could also use depiction. But these are not standard in the sense that they're not part of the core data model. It's rather extensions of vocabularies, and there's hundreds, even thousands of vocabularies defined on the web that we could use. So we'll come back to that later in the course.
Gracias.
So we can continue then. What is RDFS? RDFS, the core of RDFS is precisely what we've seen. Subclass, subproperty, domain, and range. And it's a web standard, so much like RDF. So it's what's called the W3C recommendation, W3C being the World Wide Web 3Ws consortium. So, excuse me, so the most recent version was made a recommendation in 2014. The RDF standard spans back as far as 99 or 98. RDFS, sorry, the first version of RDFS was defined in 98. In fact, it's quite old. But the newest version is 1.1, defined in 2014. So it's a web standard. It's a recommendation, which means that it's recommended for use on the web. So what is RDFS? It's precisely the core of RDFS, at least, is precisely what we discussed. We can define subclass relations, subproperty relations, domain, and range. And we can do that as RDF triples. So essentially, we just have binary relations. So we can say, for example, capital city, RDFS subclass of city. Right? So we just use this special vocabulary defined by RDFS to define this in a standard way. Has capital city, subproperty of city, family name, domain, person, has capital city, range, capital city, and family name, range, city. Range string. Okay, so we already saw similar examples before. So what's interesting here is that the range of a property, if it takes like a data type value, like a date or a string or an int, we can also define the range to be a data type, in this case, string. So that's essentially RDFS in a nutshell. It has more elements. We're not going to discuss all of the elements because some of them are more syntactic, and even some parts are not really recommended to be used so much anymore. But this is by far the most important core of RDFS. So any guesses why RDFS calls these things domains and ranges? Well, it comes from mathematical definitions. So you might have heard the terms domain, codomain, and range before. So if we have a function which maps elements of x to y, to elements of y, then we have these three different notions here. We have x, the set that serves as the inputs to the function, the set y, which serves as the potential outputs of the function, and the set fx, which are the set of things mapped to from x by the function. So we call x the domain of the function. This is like the subject of the property. We call y the codomain of the function. These are all the things that are somehow the broader set of things that could be mapped. And we called f of x, the set of all f of x, the image or range of the function. This is essentially the values. So it takes some inspiration from these, from this idea here. This is not to say that properties are functions, because properties don't map in a one, they don't map one element to of x to one element of y. For example, a property such as child, has child, might map one thing to several things, right? But essentially, this is the inspiration behind the names of domain and range. As a side note, okay. So we could look at an example of how to define an RDF schema. So we're interested in modeling an RDF schema for movies, including different types of movies, such as horror, comedy, action, some different types of people involved, such as actor, producer, director, and how they are related. Okay, so the question seems intuitive enough. With respect to how we would start to define the schema, there's no, first of all, there's no one correct answer, right? So for sure we would have, okay, a class for movie, right? So movie would be a class, we have instances of movie. So then we have different types of movies such as horror, comedy, and action. So we have two main options here. We could either define a property such as genre, and then define that the genre of a particular movie has the value horror, or the value comedy, or the value action, which is perfectly fine. Or we might prefer to define these as classes. So we might define a horror movie as a class, and a comedy movie as a class, and an action movie as a class, and then define these, for example, action movie to be a subclass of movie. Okay. Two different options, and both are quite valid. There's no real problem with either. Some different types of people involved, such as actor, producer, director. Okay, so we're going to need for sure properties to relate movies to the people that act in them, that produce them, and that direct them. So properties such as has actor, is actor of, has producer, has director. But there's some options there again. Do we define it as has director, as in movie A has director person B, or do we define person B has directed movie A, right? But we need some relations along those lines, and how they are related. So we would then define, for example, has director probably has domain movie, for example, and range person, right? These sorts of things. So one possible solution would be something like the following. And what I really want to get across here is that these definitions form an RDF graph, right? This is essentially an RDF graph that just happens to use these special vocabulary terms defined by the RDFS standard. Okay? So this is what's cool about the RDFS standard, that we can define sort of logical rules, but without using rules. So we can just use the graph itself. So what do we have here? What we've opted for in this case is to define the different types of movies as subclasses of movie. Okay? And we're defining a sort of fictional movie namespace here. So we have different subclasses of movie, and then we have these different ways in which people can participate in the movie, where we define all of these as range. So in this case, we opted for properties such as produced. Okay? So if we have produced, it means that the domain would be a person. Then we would have some person produced some movie. Okay? So produced is domain producer. In this case, we've defined these as different classes, and range movie. Okay. So directed domain director, range movie, acted in range movie, domain actor, and then we have starred in. Okay, so not just an acted in, but someone maybe who's the protagonist, plays a protagonist in a movie. We could say they starred in this movie. So that we could say is a subproperty of acted in, has domain actor, and has range movie. Okay, so there's quite a few options here. For example, maybe we don't like the idea of having to define all these classes of all the roles of all the people. So we could, in that case, just directly connect produced and say that the domain is person, directed person, acted in person. Of course, we could have animals and other things that have directed movies, for example, or of course starred in, right? So we can have animals that starred in movies. But again, we have this sort of trade-off between being more specific, less specific, and here we're choosing to define the domain as person. So yeah, so the main thing to get across here is that when we define these definitions, we form an RDF graph, and we can actually just embed these sorts of definitions in our RDF graph and help to interpret what the meaning of the RDF graph is. Any questions or comments? Okay, and so we are at 10:45, so we can take a break for a second. Okay, so we spoke about an example of RDF schema. To return to this question that we mentioned before, we might also have some properties where they're quite general. And the question is, what would we define as the domain of part of, for example? So a part of B, A could be a place, it could be a person, it could be a building, it could be many things, right? It could be a movie, it could be pretty much anything. Right? So we can't define the main person, the main movie, the main building, the main, all of these different classes, because then we would imply A part of B. In the case of A part of B, we would imply A is an instance of all of those classes, which is not what we want. So RDFS defines this general class called resource, and resource is essentially the class of everything. Okay, so it's the class that contains absolutely everything. Okay, so the class of everything, including it's the class of itself. So resource is also a type of resource. Okay, so in RDFS, in RDF, it's a resource description framework. So anything we're describing, anything we use in an RDF graph, essentially is a resource. Anything with identity. So giving domain range subclasses, resource says nothing new. Okay, so if we define the domain or the range or the subclass of resource, we don't really say anything. What we're saying here is essentially that the subject of a part of relation can be anything. Okay, or it's of type resource, but we already know that everything is already of type resource. So there's no new information with respect to that. Or if we say movie subclass of resource, we don't say anything new. If we say every movie is a resource, well, we already know that everything is a resource, so we don't really say anything new. Oftentimes, though, people will include this sort of definition to just indicate that really this thing could be used for anything. Okay. It has no real formal meaning, but it's useful as an indicator that it can be used, an informal indicator that that property can be used on any type of resource. Some other meta classes in the RDF vocabulary. In fact, this is not RDFS, but already in RDF, we can define we have defined the class of all properties, which is RDF property. So we can say, for example, has city is a property, as an instance of property. In RDFS, we then have the class of all classes. So we can say, for example, city is a class. Okay, a very common error is to maybe add RDFS here and say to say RDFS property or to say RDF class. That's a little bit of historical reason, but properties were defined. The property class was defined in RDF, and the class was defined in RDFS. Another common sort of misunderstanding is that this RDF property is a class. Okay, although it says property, it's not a property, it's a class. It's the class of all properties. Okay? So these are meta classes that we can use to find all properties or to find all classes, for example, in the RDF graph. So any questions or comments? Okay, so one thing that's interesting about RDFS is that we don't have a clear distinction between, it's not like the classes are disjoint from the instances. We can have things that are instances and classes at the same time, right? So looking at this question, would you define oak as a class or an instance? Oak is a type of tree, roble in Spanish. Yep, Joaquín.
Sí, yo creo que es ambas porque un roble americano pertenece a la clase roble, también hay otro tipo de roble, no me sé los nombres, pero hay varios,
Yep.
y al mismo tiempo pertenece a árbol.
Sí, so it's sort of, it plays the role of an instance and a class at the same time. Yeah, so completely agree. So for the American oak, I wouldn't say it is an oak. I would say it's a subclass of oak, right? So to give an example, there's this famous oak tree called the Bowthorpe oak. I think it's a very old oak tree in England or somewhere. So this is a specific tree, right? So this specific tree is a type of oak. It's an instance of oak, right? So an oak is somehow a class of these individual trees, right? But oak itself is an instance of a tree species, right? So oak itself is, it's like a member of tree species like ash and like beech and all these other types of tree species. So oak is a class, it's the value of a type, but it's also the subject of a type, right? It's also an instance. Oak is an instance of tree species, okay? What's the relation then between oaks and trees? This is the tricky one, right? And similar to the American oak part. Is oak an instance of tree or is it a subclass of tree, right? So what we say is if the Bowthorpe oak is an oak, we want to infer that Bowthorpe oak is a tree, right? So for this reason, between oak and tree, we define subclass of. So we know now that because Bowthorpe oak is an instance of oak and oak is a subclass of tree, we know then that the Bowthorpe oak is an instance of tree. So thinking about this sort of problem, I think it's always good to think of what would be entailed, what would be the inferences. So this makes sense. Whereas if we were to define, for example, that an oak was a subclass of tree species, then we would infer that Bowthorpe oak is an instance of tree species, right? Which we don't infer here because A type B, B type C, we're not going to infer A type C, right? But A type B, B subclass C, we will infer A type C. So by defining this oak to be a type of tree species, it makes more sense because we're not going to infer then that the Bowthorpe oak is an instance of tree species. So with respect to the American oak, I would say that the American oak would be a subclass of oak or a subclass of tree, because American oak is sort of like a class at the same level as oak or tree. So if we had Bowthorpe oak type American oak, then American oak would be a subclass of oak, which means that Bowthorpe oak is of type oak and also of type tree. So a little bit tricky, this concept, but it sort of makes sense if you, hopefully, if you think about what would be entailed by the definitions, right? So yeah, so it's important to note that there's no real clear distinction between these are classes and these are instances and they're disjoint, but we can have things that are both classes and instances at the same time. So tree species, a common example in general would be species of things. Any questions or doubts about that part? Okay, so here this shows a good example of the difference between type and subclass of. Okay, in this case, we will infer that a Bowthorpe oak is of type tree, but we will not infer Bowthorpe oak is of type tree species. Okay, so often there's some confusion because you read both as is a. So you could say the Bowthorpe oak is an oak, oak is a tree species, right? But there's two subtle distinctions. There are different relations that we would call is a. There is this instance relation, and then there's this subclass relation. And it's important to be able to distinguish those two. So classes can also act as instances. There's no strong distinction between these notions. Okay, so this brings us on to the topic of reasoning. So we can use these definitions to apply a form of automated reasoning over these definitions. So when we talk about reasoning, what do we mean? So what general kinds of logical reasoning can we consider? Any ideas? Anyone know of some types of reasoning? Okay, so one very vague question, okay. But there are three specific, there may be more, but some people talk about two, some people talk about three, some people talk about more types of reasoning that we could do. First type of reasoning would be an example, all movie directors are human. Anthony Ferrante is a movie director. Therefore, we can conclude that Anthony must be human, right? Based on this premise and the rule, then we must infer somehow that we must come to the conclusion that Anthony is a human. Okay, so this type of reasoning is called deductive reasoning, where we apply a deductive process, which means we make logical conclusions that are certain from the rules and the premises. They're certain in the sense that if we assume the rules and the premises to be true, then the conclusion is certain. Of course, if we apply deductive reasoning on false rules or false premises, then it does not mean that the conclusion will be true, right? So if we assume the rules and premises to be true, then the logical conclusion must also hold true based on that assumption. Okay? So there's a certainty in that sense with respect to the reasoning. So if you have taken a course on machine learning, for example, data mining, deep learning, you would have seen more of another type of reasoning, which is more uncertain type of reasoning. So for example, we could say the first 3 Sharknado movies were great. So what could we infer from this? We could probably somehow detect a pattern. Sharknado movies are great. And then we could classify this unseen 4th Sharknado movie as being great too. So it will imply Sharknado 4 will probably be great too. So there's a keyword there is probably. We don't know for certain, but we have detected a strong pattern, and therefore we have some certainty about this conclusion that Sharknado 4 will be great. So this type of reasoning is not certain. It's inductive reasoning, right? Inductive learning. Or inductive reasoning, we can talk about inductive learning, okay? It's this idea of learning approximate rules or trying to derive patterns and describe them as rules, learning approximate rules from premises. So we want to extract patterns from observations and then apply those patterns, those rules, to unseen data, to new data. Inductive reasoning. So humans perform mostly inductive reasoning. They also perform some deductive reasoning. They also perform the third type, which is subtly different. The distinction is not super clear even to me, but intuitively it sort of makes sense. So an example, Fred saw a movie with sharks and tornadoes. Sharknado movies have sharks and tornadoes. Okay. So what could we probably maybe conclude here? We could maybe conclude an explanation. We could somehow explain or find an explanation that fits the observations quite well. So we could say Fred may have seen a Sharknado movie. Now he may have seen another movie which has sharks and tornadoes, but essentially we somehow use abduction to arrive at a likely explanation for the observations. Okay, so it's a way somehow of explaining observations with something more general, or not necessarily more general, just a way of explaining a possible explanation for an observation. So this form of reasoning is called abductive reasoning, where the idea is to guess a premise or an explanation. So it's similar to inductive reasoning in the sense that what we're concluding, in a sense, the conclusion is not certain. There may be other explanations, but a reasonable explanation would appear to be that you see in the Sharknado movie in this case. Okay, so when we talk about reasoning, mostly in this course, or almost exclusively, we will be referring to deductive reasoning, this idea of making logical conclusions that are certain if we assume the premises, the rules to be true. So it's the only form of reasoning that is certain in that sense. So what conclusions can we deduce? Okay, so we have our schema of movies here. Let's take a triple. Eric Roberts starred in Sharktopus. So what could we, from this triple here, what could we start to infer based on these definitions here? So we see starred in, hopefully we've highlighted here the property. We can start to deduce quite a lot of information actually, okay? So the first thing we could see, we could go in whatever direction to start with. It doesn't really matter, but we could say, okay, starred in, so property of acted in. So we take this triple and we take this definition here, and now we can deduce that Eric Roberts must have also acted in Sharktopus, okay? So what about the subjects and the objects? Okay, so we see starred in has domain actor. So we can infer from this, looking at the triple again, that probably you've guessed it, Eric is an instance of actor, type actor. What else do we see? We see that starred in has range movie. Okay, so we see that Sharktopus must be a movie, and so on and so forth. So there's, interestingly here, if we didn't have these direct connections, if we remove this edge here, and we remove this edge here, we could still infer that Eric Roberts is an actor because we first entail that Eric Roberts acted in Sharktopus. And from that triple, we know that the domain is actor, so we know Eric Roberts is an actor. And acted in has range movie, so Sharktopus is a movie. Which is to say that somehow these edges here, we don't really need them because they would always be entailed once we move to acted in. Once we infer that triple, then from that inferred triple, we could recursively infer actor and movie based on domain and range. So thereafter, okay, actor is a subclass of person, so Eric Roberts must be also a person. Anything else of interest? Essentially, that would be everything, except for that we can also deduce a number of other things. We can deduce more trivial sorts of entailments, like that every class is a subclass of itself, every property is a subproperty of itself, all these sorts of things. So if we bring it to the ultimate conclusion of all of these things that we can derive using deductive reasoning over these definitions, we have all of this. Yeah, so we have, acted in is a subproperty of acted in. Acted in is a type property. A property is a subclass of property. Okay, property is the class of all properties, and so forth. So we have all of these sort of semi-trivial conclusions that we can derive. So the ones we're most interested in are the ones involving the terms from the original triple. Eric Roberts is of type actor. Eric Roberts is of type person. Eric Roberts starred in and acted in Sharktopus. Sharktopus is a movie, okay? And the rest are sort of more trivial conclusions. So this is actually not even the full list of all the things we could conclude, because, for example, we haven't considered the idea that everything's of type person. So we would have to add everything's of type resource, sorry. We would have to add that all of these are of type resource, yeah, which would make this a very painful graph to draw because we'd have resource in the middle and everything connected to it. So I didn't draw it. All classes are subclasses of resource. Okay, so if X is a person, then X must be a resource. This is sort of trivial because everything is a resource. So that makes person or every class a subclass of resource. Properties are also of type RDF property, so we've not added that. Oh, we have in some cases actually here. So I think what it's saying is that we should also add, for example, that RDF type is of type property, RDF subclass of is of type property, because they're all properties. So this is not the full list of conclusions, but we're mostly interested in the ones that involve the terms from the original triple. Okay. So of course, Sharktopus is just one movie. So we can apply these definitions. The idea is not just that we're defining these things for one movie, but ideally, if we were very successful with our vocabulary, we could define the semantics of data about movies across the entire web using these definitions. Yeah. So if we managed to succeed lots of people to use our vocabulary and we had these definitions here, then these could be applied equally for data describing any movie, right? So, okay, we've seen Sharktopus, but we could just as easily talk about another movie like Dino Shark, and say that we have actors, actresses, directors, and that. What can we deduce from these data when we change the movie and the actor, the actress, the director, the producer? Precisely the same information, right? So in some sense, just to emphasize that we're not defining this in the context of one RDF graph, but ideally we could define this at the context of the web if our vocabulary were completely successful. So for this reason, it's important to note that these definitions can be highly useful across the scope of the web. Any questions or comments? Okay, so how specifically do we do reasoning? How do we apply reasoning? So there are a number of ways we could apply reasoning, but the standard recommends to simply use rules. Okay, so we said at the start, okay, we're not going to use rules. We're just going to use RDF graphs. But the idea is that we can then define these sort of meta rules that define the meanings of these standard terms. So to take an example, if we have xpy, so the first thing I would like to say is you can largely ignore these rules here, which are mainly syntactic. This defines, for example, that if we have something that has the data type integer, then that it's an instance, that somehow that literal is an instance of that data type. So for 2 is of type integer, for example, but we can't have literals in the subject position, so we have to create a blank note to represent that literal, which is a little bit messy, and it's not so important. This here refers to an older form of lists, which used essentially, you could say RDF1, RDF2, RDF3 with the number to indicate a list. These were called containers, but in general, they're not widely used. So we're going to generally ignore these rules, as they're not generally used, they're not so important, but they do exist. So if we look at an example of a rule here, we have variables which are denoted with question mark, and we have an entailment. So here we have something like a premise, and then we have a conclusion. This is often called the body of a rule, and this is called the head of a rule. So how does it work? So if we have a triple xpy, then we can infer that P is a property. Okay. If we have, for example, P has domain C and xpy, then we can infer essentially that the subject of the property must be of an instance of the domain class. So x type C, x a C. So I use a the same way as the shortcut in Turtle. A is a shortcut for RDF type. So maybe we could guess what the rule would be for range. So we have P range C, xpy. So we would expect to infer. So P range C, range defines the types of the objects of a property, xpy. And we could therefore probably conclude that y is of type C. Right? So this time we're, instead of in the domain where we define the subject, we're defining the types of the objects in this case. So we have P subproperty of Q, xpy. What would we expect as a, sorry, let's quickly look. So we have xpy here. So we can infer that x is a resource. We have xpy here, so we can infer that y is a resource. We have P subproperty of Q, xpy. So we could probably guess that this would be xqy, right? If P is a property, then P is a subproperty of itself. If we have P subproperty of Q, Q subproperty of OR, then P subproperty of OR. So we had an example of has capital city subproperty of has city subproperty of has geographical part of. This implies that has capital city subproperty of has geographical part of. So we have C, a class. Every class is a subclass of resource, okay? C, subclass of D, X is of type C, therefore X is of type D. Okay? C, a class, C, every class is a subclass of itself. So C, subclass of D, D, subclass of E, what would we expect here? We would expect that C is a subclass of E. So for example, if we had capital city subclass of city, city subclass of place, then capital city subclass of place. Okay, so it's a transitive relation, subclass of and subproperty of. These are both transitive relations. Okay, so we can apply these rules. We can just apply them over and over to a graph until we don't find anything new. This is the intuition. So there are some additional triples called axiomatic triples that are always true in RDF. So examples would be type domain resource. Okay, this is sort of trivial. Type range class. So if we have A type B, then A is a resource, which doesn't really say anything interesting, but B is a class. Okay. So what we're doing really is defining the RDF and RDFS vocabulary using the RDF and RDFS vocabulary itself. Now we can't give a complete definition, but we can partially define the vocabulary using the vocabulary itself. Okay, which seems to be a slightly weird thing to do, but as a result, these triples that define the RDF and RDFS vocabulary using the vocabulary itself always hold true. Okay? So for example, we can say the domain of domain is a property. If we have A domain B, then A must be a property and B must be a class. Okay. So again, I've grayed out some triples that relate to features that are not so commonly used. We see also a definition for first and rest, which defines that their subjects and objects must be lists. So for first, it connects a list to a sublist. So its domain would, first rest connects list to sublist. So its domain and range would be list. And first connects a list to its first element, which would be, makes its range a resource. Okay. So essentially what we're doing here is defining the vocabulary in terms of the vocabulary itself. And this gives us some triples that are always true. So when we apply reasoning, what we can do is we can just add the axiomatic triples to the graph. So we are given a graph G, a set of triples, and we want to apply reasoning with respect to RDFS. So what we can do is simply apply the rules recursively on top of that graph. So we can first add these triples that are always true to G, and then we can apply the rules exhaustively, which means that until we find nothing new, adding conclusions back to G. Okay. So the question then is, will this always finish this process, or can it run forever? And if we think about it for a bit, we can think that G is fixed. It has an arity of 3. It means that it consists of triples. So at some point, if we don't invent new terms, if we don't create new terms, for all the terms that we have, we must finish when we essentially have every combination of those terms times 3, right? So if we had 5 terms and we have triples, then all we can have are 5 times 5 times 5 triples. You know, that would be all the combinations of all the terms, create all the possible triples, and then we would stop. Yeah. So 125 triples, and we can't create any more. So long as we do not invent new terms, and so long as the axiomatic triples we invent are finite, which is not trivially the case because we have these weird container membership properties as RDF1, RDF2, RDF3, where there's an infinite number of them. But if we leave those out, then this would finish. Yeah. So as long as we do not invent any new terms, and so long as the axiomatic triples we're adding are finite, then there's no problem. We can run this, and we're guaranteed that it will terminate. This is not the only way to apply reasoning. Rather than what we would call this materializing everything. So like writing down everything that is true. Rather than doing that, we could rather apply rules when we receive, for example, a query over the RDF graph. Then we could use the rules to try to find more conclusions just for that query. So there are various ways to do reasoning, but this is perhaps the most intuitive way. So we can apply rules recursively on the graph. Any question or comment on that? No? Okay, so in the lab, what we will be playing with some RDFS definitions. We'll be looking at the conclusions. We'll be using a reasoner, and what the reasoner will be doing is effectively this process here. Yeah, so we'll just be applying recursively these rules to derive new entailments or new inferences. So this is essentially the start of the part of logic. What we've defined thus far is useful. Subclass, subproperty, domain, and range are very useful semantic definitions to have, but they're only the tip of the iceberg. They're the core of RDFS, but there's another standard that extends RDFS, which we'll speak about in the next class, which allows us to define much more complex, rich semantics. And that's called web ontology language. So, but we've started to look at this part of logic, how we could do logic in the semantic web. We don't really define rules per se, rather we define data, and there are rules defined for that data. So we define data as RDF triples using the RDFS vocabulary, and we can apply reasoning then with respect, using rules, these meta rules defined in the standard, not in the data. We can apply these over the definitions in RDFS to derive these sorts of conclusions. So we still haven't actually covered these 2 rules. We can't do these in RDFS, but we'll see this in the next class on how. Okay, so again, RDFS is a web standard. The idea is that, you know, hopefully people on the web would use this to define the semantics of their data, particularly their RDF data. And it has been quite widely used. Yep, so any questions or comments? Or doubts? Okay, so if there's no questions or comments, we will chat on Wednesday in the lab. We'll play with some RDFS definitions. So see you on Wednesday.